So are we ready there, Yvonne? Great. So welcome everyone to this edition of the Physical Society Colloquium. Today we have our own Professor Matt Dobbs from the Department of Physics, and he's asked me to give a very brief introduction. And it's also convenient that he wrote in his abstract that there are no prerequisites for this colloquium, since I didn't do the homework. So Matt, take it away.
Great, thanks. Oh, I love brevity. Is anyone familiar with this book? I was guessing that you might be the only person in this room that may have read the whole thing. I have lots of dog-eared pages. Okay, this is 1,000 pages, 993 pages of cosmology theory, physical cosmology. Given the ingredients of the universe, if you can get through this book, you can calculate how you start just after the Big Bang, because as Robert's talk told us, it's hard to figure out what's actually going on near or right around the beginning. You can start just after the beginning and evolve the fundamental parameters, how much matter there is, how much other stuff there is, and see how the universe would grow. You can build universes with this. And when this book came out in 1993, to the horror of every graduate student who had to take a cosmology course, we didn't know what parameters to plug in. Or we knew some of them, but not very well. So if I open the book and I look at just about, and this book, as far as we know, almost all of it is correct. And in fact, Mr. Peebles, born in Winnipeg, won the Nobel Prize just a couple of years ago, last year, 2 years ago, for his lifelong contributions to our understanding of cosmology. Almost no one has won a Nobel Prize for their lifelong contributions, but rather for something they did or lucked into. So quite a set of theory to stand on. If you open the book, though all of the equations are more or less right, almost every plot is garbage, because they all start with assumptions about what's in the universe. For example, this plot starts by assuming that there's no dark energy, that the cosmological constant is zero. And so while you can learn a lot of cosmology from this, you can learn very little about the universe. In order to get from here, largely to correct, to what we know today about the universe, which is an incredible amount, we need measurement. We need technology to cast onto the sky and see which versions of this, see what the fundamental parameters are, and learn about the world in which we live. So it's really important, this interplay between theory and experiment. And most of what we know about the universe when this book was written, we did not have the technology to measure. It wasn't just that he had a great idea, let's go look. He had a great idea, many of them, and many, many people do. I'm giving him more credit than just one person should have. And a whole community of people went out to build the detectors, the telescopes, the particle physics experiments that tell us what we know today about the universe. So a great interplay that we've always had between theory and experiment, and one where, in this case, the theory was way, way ahead of the experiment. What drive?
I should also add that Mr. Peebles will be this year's McPherson lecturer.
Is he? Oh, fantastic. He's so much fun to talk to. When is that?
March, I believe, right?
In March, he'll be right here, and we can all talk to him and get upset about having to read all 993 pages in John's class. Okay. I hope that every one of you, when you go to the lab or sit down at your desk or in front of your computer, does so knowing that you're working on the most important problem in science to you. For me, some of the most important problems in science are ones that I get to work on, and I'll just share a few of them with you. I'd love it if someone throws an example right afterwards of their favorite problem. This is what we know about the evolution of the universe, and this is just like the plot I showed you in the book, but this one's more or less right. We have observational evidence throughout the history of the universe. It starts back here near something like a Big Bang that Robert talked about a few weeks ago. And then it evolves through a period of rapid accelerated expansion, inflation maybe, to produce the image that we've made and we know is true of the cosmic microwave background, the leftover light of the Big Bang, just a tiny fraction of the age of the universe after the start, 380,000 years. And then it goes through an evolution where mostly the universe is just uniform, a little bit of overdensities and underdensities, and eventually gravity causes things to collapse and stars start to burn and we start to produce other things besides just the helium and hydrogen and lithium that's there, until we form galaxies and so forth. And we continue along this boring expansion until almost today, about half the age of the universe, when it starts to accelerate in its expansion again, which we've measured and seen kind of directly, and we can't really explain very well to get out to where we are here today. So in order to explain that, of course, we have to put in the constituents of the universe, what it's made of. This is what Peebles didn't know when he wrote his book. We have to write down how much regular people-like stuff, planet-like stuff there is. We have to write down how much dark matter there is, stuff that is producing gravity, but is not something we can see directly with our telescopes. And then, of course, this energy density in the universe, dark energy, which is constant no matter how the universe expands. Weird stuff that we, understand well enough to write down and characterize, but we don't understand it all in terms of knowing what it is. One of the questions I'm really excited about, of course, is dark matter. And you probably hear me in other contexts talk about axion dark matter, one of my favorite things on the particle physics side. It turns out that in cosmology, there's up on the sky, there's actually a lot of room for dark matter to be just boring. From all the measurements we've taken of dark matter, we know a lot about its properties on the sky, and we've eliminated the possibility that all of the dark matter is made of, let's say, something normal. For me, normal is black holes. Normal, like ordinary matter, collapsed into black holes. For just about every mass of black holes, by these projects or experiments or telescopes, so long as all of the black holes are exactly the same mass. It's like saying every star up there is exactly the same mass. All of the white space down here is the fraction of the dark matter that could still be just regular black holes if they're distributed over different masses. So an example theory is one of primordial black holes that is this red curve. It fits everywhere in the white. And it could well be that all of the dark matter mystery on the sky is just because there's black holes hiding everywhere in the universe of masses that are very much like our sun, between about 1 solar mass and 100 solar masses. They could be out there masquerading around the universe, and we don't yet have direct observational evidence that excludes that. It could be a boring explanation to what's going on in dark matter. This is one of the mysteries I'm very keen to shed some light on. Another mystery that I'll talk about towards the end, I hope if there's time, is just how it started. If the universe began in a Robert-like scenario without inflation, it gives us certain observational evidence that we may have a handle on in the next decade. If it went through just boring inflation, we have a different observational evidence, which I'll touch on at the end. So I'd love to learn about that question too. How did it start? Was there a Big Bang-like thing, and what does that mean exactly? Finally, another thing I'm really excited about is this period of dark energy, this period when the universe starts to accelerate in its expansion again, speed up in its growth factor. And we, as I've said a moment ago, we know that this is happening through direct measurements, but we haven't actually watched it happen over time. We're inferring what this curve looks like over a long time scale, and there could be hints in there as to what physics drives it. Did we get the equations of gravity wrong? Was there some particle that maybe is related to something else in the universe, like maybe the dark matter, that is annihilating and injecting energy somewhere? There's all sorts of ways that you can inject energy in the universe to drive this, and that's something that we hope to see directly. I talked about the cosmic microwave background, like the foundation of cosmology observations today. The dream I would have to go after that is to see the fluctuations here, and instead of just seeing them at one time in the history of the universe, to watch them evolve, to watch them grow and trace them through all time. To me, that would be the best direct way to measure the evolution, the growth of the universe, rather than what we do today, which is we look way back and see the cosmic microwave background near the birth of time, and we look right in front of us and we see the effects of the cosmic microwave background through the growth of galaxies and other structures. So I'll talk a little bit at how our dream of measuring this more or less directly through 21 cent here. Yeah, actually, I'm going to come back to this a little later. The final mystery I want to touch on, I will be touching on in the technology part of this talk, is this phenomena that we see across the night sky. If you had radio eyes, and that's all you could see, several times per day, actually about 1,000 times per day, you would be looking up at the sky and you would be blinded by a flash of light, by a fast radio burst exploding on the night sky, overpowering all the other light on the night sky, with a duration of about a millisecond. We've learned a ton about where these come from, what they're like, and how they illuminate the universe, but we don't really understand the fundamental physics of what could produce them, or indeed, how to explain all of the phenomena we see. And so, this is another great mystery for me. And what's represented here is just the night sky turning, because of course the Earth rotates, and one possible telescope being that every once in a while we'll pick one of these up. Okay, so let's get at how to track down these mysteries, how to attack these things. For me, I have a dream, and I think most of us do that are in astronomy, of building the ultimate telescope. Other people talk about the Habs games over beer. We talk about the ultimate telescope and how to do it a little bit better. We compare our telescopes, of course, and try to figure out whose design is going to be best. And then we get them on the sky and we characterize them. And we brag about, exactly what this telescope can do. For me, the ultimate telescope would be something that adds very little extra noise or garbage to the night sky. So when you look up at the sky, you're recording photons, and there's a fundamental noise to that because the number of photons that arrive per second from a source, our sun, for example, is a statistical thing, and it fluctuates by time. And even if, like, everything else is perfect in your experiment, you're going to have some random fluctuations in your measurement. If you could ever get it such that your telescope itself was accurate enough that its noise was lower than that, you would have a sky noise limited sensitivity. And actually, we're there. We're doing that in our millimeter band CMB experiments. It'd be cool if we could get there in the radio. We're a little ways away. It'd be great to be able to see really small things on the sky. Instead of taking those blurry radio images that most of us use, like the cosmic microwave background ones, it would be great to be able to focus in and see very, very small things and very large things. Even though I want to see really little things, I want to have a huge field of view. I want to see the whole overhead sky all the time. I'd like to see it panchromatically across every possible color. If there's blue colors and red colors up there, I want to see them. This is a radio telescope, though. So if there's megahertz signals or gigahertz signals, I want to see those all at the same time. So I'd like to have a large bandwidth. And then finally, I don't want to take pictures. I want to make movies. And so I'd like my telescope to record images of the sky very, very quickly so that I can see changes. And today in astronomy, we're really going through a change where many of the very exciting measurements that are taking place are of transients and things that are changing on the sky. Unlike the last century, where almost everything that was groundbreaking, well, I'm not very accurate on that, but many things that we recorded were static images of the night sky.
What is ultra fast in your field? In my field, that's out of.
Yeah. Sorry, you've got us. You've way got us. but for us, really fast for a telescope, a radio telescope would be microsecond. Yeah. But we measure attawatts in power. Great. Okay. In the old days, the last century was dominated by really big telescope dishes. This is actually a relatively new telescope. It's in China. It's called FAST, and it's 1/2 kilometer in diameter. It is immense. Care to share with the crew?
No. Very much not. Not in the same age.
And not necessarily in this telescope, but in most single dish telescopes, or even most interferometers, where we have dishes that are separated from some distance, the feed, the antenna that picks up the light, and the amplifier that follows it, it was really important to get that to be as low noise as we could, to be below the sky background limit. And to do that, we had to take the amplifiers and we had to cool them to a very low temperature. So it was very common when you put just one antenna on the sky, one pixel in your camera on the sky, to spend as much as $1 million on that pixel so that you could get it really cold and make it very accurate. That was like the last century in radio astronomy. Today, and remarkably not driven by university or government labs, we're able to build amplifiers that have the same noise performance as those cryogenic ones and sit at room temperature. And you all probably have something similar in your pocket in your cell phone, and certainly it's up there on the communication towers. And they cost like dollars each. The $1 million amplifier that we used to build 20 years ago today has a cost that's literally a couple dollars each. So the types of telescopes we end up dreaming of building or actually getting on the sky are very different. Last decade, people spent all their money on the mechanical structure to build a big dish and put an expensive pixel to capture the light. Today, we don't want to spend money on metal anymore. We put antennas everywhere. We have many, many telescopes that are cheap, and we run them together with big computer backends. And that ends up being very powerful, and I'll show you why. And I'll show you why right now, because the next goal is not just, if you have a great big dish, what you're able to see is governed by just simple optics, diffraction, lambda over d. We're talking about wavelengths for me right now that are about half a meter. And so in order to see something that's 1 radian on the sky, lambda, the wavelength, half a meter, to see 1 radian, I would need a half meter dish. A radian's like huge, right? That's not even interesting. If I want to see something that's a degree on the sky, I need to be 20 wavelengths long, and we're already at 20 meters. So how do we see, oh right, so I have this big dish, I spend a lot of money on it, and I put just one antenna at the center. That means I'm zooming in on a little piece of the sky, and that's all I see. In order to map out something, I'm going to have to scan my telescope around in order to record the image. And you've got like a really cool telescope if you have 10, 12, 16 feeds at the center. It's not like a digital camera that has megapixels. A dozen pixels is like awesome on these single dish telescopes. So let's do it an entirely different way. And I think many people here have already spent some time listening to stories about Chime, our cylindrical telescope that we built here in Canada. But let me show you how we use antennas, and many of them, instead of a big dish, to reconstruct an image on the sky. And as you can see from this drawing, Chime is not a traditional telescope that is just a round satellite-like dish. It's cylinders like this, and it collects light in a different way. Let me take one of these cylinders, and I'm going to put a single antenna. Antenna, don't worry about it. It's just the thing that collects the electromagnetic radiation. It's just the thing that turns the light into an electric signal. And I'll put it at the center. I'm going to stretch this cylinder out, and in one direction it's curved, so it means that I'm just looking straight up in that direction. In the other direction it's flat. It's just a mirror, so I get to see everything from horizon to horizon. And so if this is the night sky overhead, what I see on the night sky is this hot dog. Not only that, what I see on the night sky with one feed is everything that's in this hot dog added together as one electric signal. I cannot distinguish between a signal over here or one over there. I see the sum of them all. Bad, no one would do this a while ago. However, if instead of that, so I'm going to take this, I'll put it on the night sky, here's my hot dog, and then every day the Earth's going to turn. And so you can see that while I can't tilt or turn this telescope, I can see different regions of the night sky. Because I am not at the North Pole, it's not rotating around me, and because I'm not at the equator, it's not just rotating by me, but instead the North Celestial Pole is up here. That's probably why you're tilting your head. And the Milky Way, this beautiful thing, is spinning around us. I take my one single feed, I get my hot dog like before. If instead of one feed, in this example I put 16 of them down the focal line, and I record the electromagnetic field in each of those 16 feeds, and I actually record the whole field, the phase and the amplitude of the wave, everything about it, fast enough that I can actually see the signal rising and falling. In this case, if it's 21 centimeter light, it's 1420 megahertz, so I'm sampling it at about 3 gigahertz. When I combine that together, I can put it through some signal processing. Turns out it's just a fast Fourier transform, and I can point the telescope digitally. I can look through each of 16 degrees of freedom. I can simultaneously see in these 16 different directions on the night sky. Okay, so that's letting me get after this dream, because now I'm seeing from horizon to horizon with that flat mirror. By having lots of processing power, I've curved it up with the cylinder on the sides only because the government didn't give me enough money to have a feed line that's two-dimensional. They only gave me enough money for a one-dimensional feed line. But, if we're really good at this, maybe they'll pony up for the next version. Okay, and then if I build more cylinders, in the case of Chime there's 4 of them, and put feeds down each of them, I can take this hot dog and I can divide it up into 2 dimensions. And there are precisely as many different degrees of freedom, places that I'm looking on the sky, as there are feeds here. And in the case of Chime, Chime is a telescope that has 1,000 feeds in it. It looks in 1,000 different directions uniquely. You can look anywhere between these two by co-adding these. It's just not a unique degree of freedom. Okay. So some of you may have been over to the site in Penticton, British Columbia to see the Chime telescope. This is an aerial view of it. It would be really good if you had a snowboard in winter. And it's also really good for the type of astrophysics we do, which is doing large surveys of the night sky, seeing a lot of the night sky to go after our science goals. An example of one day in the life of Chime is this image. This is the sky overhead as a function of local time. So at 6 o'clock in the morning, we see this stripe. And then by the time it's 8 o'clock, this stripe has risen overhead and we move across. And so each and every day, we see the entire overhead sky one time. This is good because if we're mapping the sky, we can make very precise maps. We can take the same image day in and day out, find the things that are probably just people talking to each other on their cell phones and throw them away. Find the things that are static on the night sky and map them as large-scale structure. And also, equally importantly, look for things that are rapidly changing. Things that change day by day, sure, but also things that change while the sky is in our field of view. And those are the fast radio bursts that we're really interested in, things that go boom and bang on the night sky. This map is just the raw data, so there's lots of garbage and features in it. Like, here's the sun. It rises and it falls, it comes into our beam. We have side lobes, so in the same way that you have a single slit experiment, our cylinders are just like single slits in your quantum mechanics class or in your optics class. We have the ripples that go on the side of it, and it looks like this. And unfortunately, at some wavelengths, we aren't able to Nyquist sample the electromagnetic radiation. We aren't able to sample it more than half a wavelength in every direction. And so we actually see an aliased version, a second copy of the sun that looks like it's coming from the other direction. We can sort all these things out because we know what the telescope does, and we spend most of our lives just characterizing it. So after a bunch of processing in different nights, we can co-add the information and start to make very accurate maps of the night sky. You can see this one isn't perfect because there's still some striping here. You can see things on the night sky that can't possibly be there, but most of the detailed astrophysical features are preserved in images like that. Okay, so what are we going to do with this thing? We might eventually get to the point where we have the ultimate telescope. This is just a gross approximation of it, but it's meeting some of the key things, and it's kind of the first of its kind along these lines. It's seeing a lot of colors because it has a very broad bandwidth. It has many different frequencies it sees. It sees all of the overhead sky from north to south in the cylinder direction, but not quite all of it in the other direction. But then we just spin the Earth around every day to see the rest of it, so that's okay as well. And it turns out that it can take very fast images, though Peter will laugh at us because he's ultra fast. What can we do with it? Well, let's start and look up just in this direction. And when I look out, the first thing I see is our own Milky Way, our galaxy. And you know what? Everything in the universe, to first order that isn't dark matter, is hydrogen. Right? 3/4 of all matter in the universe is hydrogen. So the first and the next quarter is basically helium, and then there's all those other stuff astronomers that look at that burn at the core of stars and create emission lines and so forth. But to first order, the simplest thing you can see in the sky is where the hydrogen is. And hydrogen is a perfect, amazing atom or molecule because it's just a proton and an electron. Sorry, these are the spins. And when it gets excited, they align. You have to inject a photon to do that. It might absorb a photon to do that. And then if you wait about 10 to the 7 years, on average, that atom will decide to de-excite itself. And when it does that, it's going to emit exactly the amount of energy that separates this hyperfine splitting, and a 21 centimeter wavelength photon comes out. 10 to the 7 years is long for a typical PhD at some universities, but the hydrogen, there's a lot of hydrogen in the universe, there's a lot of hydrogen in each star in each galaxy. So though your probability of seeing an atom flip is low, your probability when you look at 10 to the 20, 10 to the 30 atoms in a galaxy, a lot of them flipping is really, really high. In fact, the sky is just a shine with 21 centimeter photons. So when I look out through my telescope, the main thing I see is emission at 1420 megahertz, which is exactly 21 centimeters, and that's just the Milky Way. And I'm a cosmologist. I want to see the universe, so the Milky Way is in my way. I'm going to ignore it. When I look out in that direction, though, far enough, I see another galaxy, NGC 3419. It, too, is just hydrogen to first order. And so it's emitting 21 centimeter light. But it's far enough away that when that light was created, was a long time ago. By the time it got here to me, the universe has grown and it's redshifted. And it sits at about 21.2 centimeters, or 1410 megahertz. And so I can see out in this direction that there's a big hunk of hydrogen nearby. And there's another pretty big hunk of hydrogen that's out at a redshift of 0.01 or something, at an expansion history of the universe of about 0.01 or something. And it turns out that this old bad telescope, this is just noise from the telescope, but if I had a really good telescope, or if I made many observations over a long period of time by looking at a lot of the sky, that what I'd see in here is all the other matter that sits further away than this galaxy, or between this galaxy and the Milky Way. And that's really our goal with the cosmology side of Chime, to map the location of all the hydrogen in the universe as a function of where it is on the night sky. And because it's redshifted, it follows the expansion history of the universe as a function of how far away it is. Great, so let's go back to this map. This is one of our Chime maps, and it's at 680 megahertz. And we have these across 400 megahertz of bandwidth. We have them across a huge history of the universe in terms of the 21 centimeter redshift. From when the universe was about a fifth its present age, the light has been stretched to 1.5 times its, am I doing the math? 2-ish times its length, to 800 megahertz, which corresponds to a redshift of 0.8. These are redshifts Robert's very interested in as he tries to understand dark energy, because it's the time when the universe transcended from one that's just expanding normally, what you'd expect without dark energy, to when the energy density of everything else in the universe fell low enough that dark energy took over control, the steering wheel, and drove the universe to accelerated expansion. We know that something like that happened because we see the accelerated expansion today, and we see before, but we haven't really traced that turn on. We haven't watched it happen. And we hope there's something in there about what drove that expansion. So here's one of our maps, and we have maps like this that are at each frequency, or said differently, at each history in the epoch of the evolution of the universe. So let's take our knowledge about a 21 centimeter, and really what we end up doing then with our maps is making onion-like shells and figuring out where the hydrogen is in the universe. I am completely oversimplifying it, because we have to calibrate our telescope to a part in a million to do this well. And because sitting on top of all this 21 centimeter emission is the other emission from galaxies, like synchrotron radiation and so forth, that has nothing to do with the 21 centimeter signal. So it is going to be hard. But I will show you some of that towards the end. So basically, by looking at the wavelength of the light we record, the 21 centimeter light is right here in front of us. The 42 centimeter light is at a redshift of 1, where essentially we start looking with Chime. If we had a really big antenna so that we could see 2.1 meter light, Chime doesn't do that, but Cynthia and John work on telescopes that do that, and Adrian, we would be looking all the way back to redshift 10. If we had a 21 meter antenna, we'd be looking back to redshift 100. There's hydrogen there. It's out there to be found, but we can't afford to build telescopes that have antennas that big yet. And if we looked all the way back to 210 meters, we'd be looking at the hydrogen that sits there on top of the cosmic microwave background at a redshift of 1,000. This is the dream that we have. No one to date has looked up at the sky and made a map of large-scale structure with 21 centimeter light only, including us. We built the experiment to do it. We're on the path to doing it, but we haven't done it yet. This is new stuff that we hope to achieve. To do it, we need a lot of technology, and unlike the other experiments I've worked on historically, most of the technology is just about seeing what's out there from others that have built things, from the communications industry and so forth, and refactorizing it in different ways to make it suitable for radio astronomy. This is the antenna we use for Chime. That's an antenna like your car antenna, but it's tuned to be very broadband, so it can see signals that are that range from 400 megahertz to 800 megahertz. This is an old prototype. And you see, really what we've been trying to do here isn't like the high-tech stuff you usually think university labs should do, but to take regular, everyday materials that are really cheap. This is a printed circuit board. It's made in a place that would build a circuit board instead of an antenna, and make it, mass produce it, make it cheap enough to fill a telescope with it. So I don't know if people want to see these things, but I can pass them around. Sitting on the other side of it is a set of electronics that we build right here in Montreal, in private industry next to Montreal, but all of the design is done in-house here in the physics department. And these boards capture the signals, they capture the electrons that are flowing down the wires, they digitize them at a really high rate, and then process them to form those beams. In Chime, there's about 128 of these circuit boards, and together they are processing the same amount of data that all of Canada is using in terms of its internet traffic. So, you know, there's other technology that does that. Your cell phones are doing it all collectively together. But our challenge was to take that technology, put it in one place, and make it work together in a way that could process a tremendous amount of data. It is presently the world's largest radio correlator. That is the largest correlator that takes astronomical signals. And it has a budget that was about 100 times smaller than the next one. That mass producing factor becomes very important. Okay, rapid exposures. Why do we care so much? Remember I was talking about fast radio transients, fast radio bursts. These are these explosions of light, and we don't really know much about where they come from. We've learned a lot more over the last couple of years. And when they go off, they're really far away. They're halfway across the universe, and they're an explosion of light that's at many, many colors, often spanning the entire color spectrum of Chime, the entire frequency spectrum. As the light crosses the universe to us, the universe, of course, is not a vacuum. The universe is a prism. It has electrons in it, and so the speed of light through the universe is not Einstein's c. Instead, it's c divided by the diffractive index, and the diffractive index is different for different colors. So when light travels across the universe, the high frequencies, the small wavelengths, move faster than the long wavelengths, just by a tiny, tiny, tiny bit. So that when this fast radio burst is produced, all the light is lined up. It's an explosion that lasts a millisecond, and then it goes across the universe, and the blue colors get here first. Here's a spectrum. This is the very first FRB that was detected and seen and recognized. It was in 2007. The high frequencies, the bluish colors get there first. They arrive at the top, the black line here, and then trailing along behind it are the other frequencies, slower and slower, right? And it has a characteristic spectrum. The curvature of this line is just given by your basic physics. It has nothing to do with astrophysics. And they're actually really hard to see. They brighten the whole sky, but your telescope, rarely did a telescope ever record data at a millisecond or a microsecond. We always integrated 30 seconds, a minute, gone. When we did record fast, we typically looked at all frequencies at the same time. So it's very hard to see the difference between this chunk of data from top to bottom and maybe this chunk over here where there's a little hot spot there, right? It was only when we took the data, well, these guys got lucky. They recorded it all and processed it offline and eventually recognized the signal. Today with Chime, what we do is we look through each one of those 1,000 different pointings on the sky, and we pipe all that data through a mega computer, and we try all different dispersions, all different slopes of this line. The equation of the line is known, but the slope depends on how far away it is. And with each of them, we basically take the line and bring it back here for all possibilities, and then test that as a signal to noise thing. And by doing that in real time, we're able to trigger and record the data for the fast radio bursts that come through. So I'll show you some of the science we can do with that. This talk largely sounds like it's about technology, but I do need to stop for a second and remind us all that there's really no such thing as like intelligent or smart technology. There's just smart people that have ideas of how to build it. And at least in the case of Chime and all the technology we work on, a lot of the smarts comes with from people that don't necessarily have all the experience. There are lots of great innovations and ideas that come from young and old people on purpose and by accident. So I just need to ground us in that. Okay, so we end up having a sky that's like the one I started by showing, but now we've cast a huge beam on the sky and we're able to divide it up. And then we built this big computer that sits behind it. And lots of people here in the department worked on that big computer and on this telescope. Who here in the room is involved with Chime and Chime FRB? There's at least some faces here. Yeah, so all these are people you can talk to afterwards and learn more about it. Great, so we have the possibility of seeing this. And about a year ago, we released the first catalog of fast radio transients. At this time, people had seen about, 30 or 50 of these. And in this one paper that spanned less than a year of data, we released about 500 fast radio transients. So we're taking the field from the ability to see weird things and talk about them over coffee, to do detailed statistical analysis of what the populations look like, to see how fast radio bursts in general behave, how they're correlated with structure in the universe. Do they come from certain places? Are they correlated with where galaxies are or not? What could their sources be? And then start to highlight weird ones, things that have properties we'd like to further study. This is the one I showed you before. And it's light that was all emitted at the same time, but because of its transfer across the universe, the longer wavelengths take longer to get here. We process that and we move it back to make something called a waterfall plot. Here's a waterfall plot of a very famous fast radio burst. This fast radio burst has two peaks of intensity. So here I've taken this, I haven't. Many of the people in this room and others in the department have written the software and the code to take this and try all possibilities and find the one that lines up this line best. And you see two emissions. The integrated emission is up here, and there's almost no correction for the telescope itself. It's kind of embarrassing. Our telescope has a lot of ripple. Most of the effects that is ripple in this direction is because of the instrument itself, and we correct for that later offline. This fast radio transient, this fast radio burst is very famous because it comes from inside our own galaxy, unlike the vast majority of them, and it lines up near perfectly with a magnetar. So there's a lot, you can start to speculate about the population as a whole and other ones. The other reason I grabbed this one and threw it on the screen is that it has two pulses. It's not a single explosion on the night sky. It has two rapid pulses. What could produce two rapid pulses? I'm not looking for the expert opinion at all. Just pulsars do it. They're spinning. A beam comes in and out. Absolutely. Yeah. It could be that whatever amazing astrophysics produces this much energy in such a fast time scale. I'll bring it over. Oh, okay. You can have some of my stage space. That we don't understand that astrophysics very well. It's probably some jet-related astrophysics as well. One of the things that excites me about things that have more than one pulse like this is the possibility that the source itself produced just one pulse, and perhaps in getting to us, it was turned into two pulses. We don't have direct evidence for that right now, but it's one of the things that could allow us to probe other physics in the universe, physics that the non-astronomers care about as well. Imagine that that fast radio burst is not this. Because we know where it comes from, we've associated it with an object, we know what sits between us. I just grabbed it because it has two pulses, and if you Google search fast radio burst, it's one of the first to come up. He's really famous. It could be that light, created halfway across the universe, is produced and travels very close to some very massive object. And if you spend some time with Peebles' book, pages 400 to 632, I'm making up the numbers, but a lot of pages. You'll know, of course, that the light is going to be bent around the object. The light is going to be bent around the object and follow the curved geodesic of space-time. And then if the impact parameter, the alignment of your line of sight with the radio transmit with respect to the lens, the black hole, is close enough, not only will it be bent by the gravitational pull of it, but there'll be multiple paths that go by that object and arrive to us here on Earth. It will be gravitationally lensed. So the slide here is Zarif's slide. There he is. He can tell you a lot more about this stuff because it would be a 2-hour talk in itself. But what you'd expect to see then is you'd see the fast radio transient along this path, and the path that provides the most magnification. The lensing increases the signal as well because it brings lots of sky area into focus down to a small region, would arrive first. And the other image, there's often two images, there can be more, the other image would have a smaller amplitude later on. And if we can figure out that this is going on, we can learn about these lenses. We can probe, we can look out at the night sky and see things like dark black holes that are robed from other things. And learn about maybe that dark matter that is a cloud around a galaxy is actually little dots of black holes. We can probe them more or less directly by making images like this and figuring out if this signal and the one that came after it are actually the same. To do that, we actually have all the information we need because our telescope records not just the intensity of the light, how bright it is, like every telescope at high frequency can only do, because they can't record both the amplitude and the phase due to quantum mechanics. We're a low enough frequency that the quantum mechanic noise is small, so we get to record everything. And it should be that image that passed on the left of Bill and the right of Bill to be lensed together, it should be a copy of the exact same signal, modulo some nasty effects with propagation or whatnot. But the amplitude and the phase as a function of time should be the same. And we can look directly for that. So what we need to do to tease that signal out is do a time lag cross correlation. People are familiar with correlation, of course. For example, is the rate of people going into bars on St. Lawrence Street the same as the rate of people buying Timbits? Day by day, when more people go to bars, more people buy Timbits. Right? Okay, but if you study that on the minute time scale, when the peak of people going into the bars goes up, the Timbit rate doesn't go up because they're in the bars. But if you take that peak of people going to the bars and you translate it by 2 hours, it lines up with the purchase of Timbits. There's a time lag correlation between the purchase of beer in St. Laurent Street and the purchase of Timbits down the street. That's a time lag correlation. And if the Tim Hortons people are smart enough, they will measure the rate of beer consumption and figure out when to open their Tim Hortons nearby. Time lag correlation. That's exactly what we can do here. We can take the actual waveform, translate it in time, and see if it lines up. If it does, it'll look something like this. This is the first fast radio transient. This is the second. You can't tell and I can't tell if it's exactly the same waveform. But if we take a copy of this and we move it on, and the whole time we multiply it by here, every single point, then when this lines up with itself, of course it gives a correlation of 1, and it is the same. It is the thing you're correlated. By the time you move it over here, it creates a huge peak. If, on the other hand, it's like that fast radio burst I just showed that was from the magnetar that is not lensing, that we know it's not, when it gets over here, this signal will actually be different in its random looking fluctuations, and you'll get no correlation effect here. Or you'll get a slight correlation in both directions that's just because of the excess power. So that's our time lag, a correlation possibility. I'm not going to show you results from this yet. We're working on the first paper with it. It basically shows all the techniques to do this cross-correlation and how to cast that on the limits of how many primordial black holes there are in the universe. Spoiler, it's not a super exciting result yet in terms of detecting things, but it's the framework that as we get more and more thousands of FRBs, we start to be able to set useful limits. This is really exciting because you've seen images of lensing like this, right? In part of our GR, we look at images of gravitational lenses like this. This corresponds to different path lengths of the light that gets to us of the scale of a year. You have to have an enormous lens to see anything, which is why nobody can exclude the possibility of 10 solar mass black holes being out there, because it's not big enough to produce this type of lensing. The time delay between the two images is a year. There's other types of lensing. By the time we get to the work that we're doing with Chime, the time delays that we probe are milliseconds down to even nanoseconds. So you can have a very small gravitational effect and still detect it. And that's why this sort of technique would be sensitive to those very small black holes that wouldn't normally produce images like that on the night sky. Okay, let's get back to our map of the night sky and do some, I didn't show you any cosmology results, but I'm just showing you cosmology with fast radio transients. Let's look at sort of the bread and butter cosmology. This is a map of the night sky again, the same one I showed. And in order to make this look pretty, to get rid of the rings from the sun, the side lobes and so forth, we have to have really good understanding, a really good understanding of the telescope itself. This is a map that we make of how our telescope sees the sky. It's pretty, isn't it? It's pretty, but it's really complicated and there's big error bars on it. That hot dog I showed you actually has quite a pattern off to the side. And if we know this perfectly, we can take it into account. So this plot is made, with most telescopes, you take something bright on the sky and you just scan your telescope across it, and you'd learn how the telescope sees in its side lobes and so forth. We must have forgotten about that when we built Chime, because it lays on the ground and it can't move. So we have to find sources that move across. The sky rotates, but the only astrophysical object that both goes across your field of view and rises and sets once per year only is the sun. Right? In the winter, it's very low. In the summer, it's very high. So we can watch the sun go through our beam, and we can trace out and figure out how our telescope sees the sky, and piece together both how it sees it up here and down here, which we can't do with normal astrophysical sources. There are dozens of person years that go into characterizing the telescope. With that, we can take our maps and deconvolve them, take out the effects of the beam, and learn about the night sky. The main thing that we're doing right now is learning about the night sky with objects that other people have told us are out there. So this is our Chime map in the background. This is how we see the sky. And the hatched regions on top of it are surveys from the Sloan Digital Sky Survey of where galaxies, quasars, and so forth are that they have found with their dedicated surveys. And their surveys see things, this is a histogram versus redshift of what the Sloan Digital Sky Survey, a data release 16, sees. They see quasars out to a really high redshift, 2.2. This spans the entire Chime band. They also see other galaxies at lower redshifts. And we can take our data and cross-correlate it against those galaxies. Everywhere in every direction there is hydrogen, but in the directions where there is a big galaxy, there is a lot more hydrogen. And in fact, since they know where the galaxy is, and they tell us exactly how far away it is, even in the units we want, which is redshift, then they can tell us which map to look for the hydrogen from that galaxy in. And so that's the first step of what we do. It's really complicated to look for the 21 emission signal itself because of these foregrounds, because of other things that produce radio light, especially like this computer and your cell phone, thanks a lot, but also because every astrophysical object will emit radio light from other means. So the result that we're putting out right now is one where we look in the direction of each of the many thousands of galaxies in the Sloan Digital Sky Survey. We cut out a thumbnail in that direction, and we choose the frequency in all of our maps that corresponds to the correct redshift. Then for each of the many tens of thousands of galaxies, we stack them up. And what we end up with is an image that looks like this. So this is, I forget whether it's 38,000 or something galaxies, all stacked up together. And what you're seeing as the red dot is the hydrogen that is the collective amount of hydrogen in all of those galaxies. We can, of course, then go to the Sloan Digital Sky Survey and ask them what they know about those galaxies and start to learn things like how much hydrogen is there inside the galaxy versus in the rest of the universe. What is the bias? How does hydrogen collect in galaxies versus outside? And what is the total amount of hydrogen that goes into people's models for the evolution of the universe? This is the first time that anyone has detected 21 centimeter emission at this high redshift. And it's kind of the building block. We're skipping the step of needing to exclude all the false signals because we're knowing which ones here are correct. We've also excluded a lot of other correct signals as well. So this is the stacking result that demonstrates that we're able to see hydrogen in the universe and allows us to measure how much hydrogen there is and what the bias, what the association with galaxies is. The next step for that, of course, is to collect that and use it without a hint from someone else. We want to see the galaxies they don't see. We want to see all the galaxies that are too small for them to see and add them up so that we can measure the scale of the separation of them. The cosmic microwave background peaks, the spots, which are there in galaxies as well, as a function of redshift, and see the evolution. We're still quite far from that. Okay, where do we go from here? Where do we go from here in terms of the technology? The next thing that we're working very hard on, and most of the people up in the labs upstairs are working on right now, is the follow-on to Chime. The Canadian Hydrogen Observatory and Radio Transient Detector, whatever, is the thing that spells CHORD, which seemed appropriate after Chime. What CHORD is an array of about 500 radio telescope dishes. Each one just has one pixel at the center, but instead of there being a feed line inside one big cylinder like this, think of each of these as like a glorified antenna. and it together is a two-dimensional thing that creates a spot on the sky and then divides it up into many, many beams. So that this thing is looking in 500 different directions at the same time. And most importantly, it's quite a bit broader band. It can see even more colors, a factor of 3 more colors than Chime. In Chime, we're also building outrigger stations, so distant cylinders that together allow us to see very, very small objects, and there should be a whole talk on that sometime to learn about both the physics and the observations of it. And we're doing the same thing for CHORD. So that in addition to our site in British Columbia, there'll be a site in Green Bank, West Virginia, and a site in Hat Creek, California that houses these telescopes. Our goals with CHORD are, first of all, fast radio transients, to see them with better resolution across more colors, to better understand where they come from and what they are, but also to start using them for the first time as cosmological probes, to go after the dark matter, to see the evolution of dark energy and so forth. We're looking for really bizarre pulsar-like objects. We would love to see a pulsar orbiting around a black hole, because there's portions of Einstein's equations that we can probe there that are basically inaccessible elsewhere, and that's very relevant now with LIGO seeing the coalescence of objects like this. And to look at how neutrinos affect the growth of structure in the cosmos. Finally, the goal of mapping the location of all of the hydrogen in the universe out to about a fifth of its present age is first and foremost, and that has really driven the design of the telescope itself. So, all in all, the CHORD experiment, it's about 2 times the collecting area. The total size of it is about double. It has 3 times the bandwidth. And because the performance of the amplifiers is better today, it's about √2 better in its noise performance. And if you multiply those numbers together, some coarse figure of merit would be a factor of 10 improvement in terms of detectability of some things. So this is the same site you saw before. These dishes don't exist yet, but they will be laying in a field next to Chime and conducting a survey adjacent to it. One of the key technologies, people laugh at us. They say, you know, Canadians, you just go around building fiberglass canoes. One of the key technologies is that the dishes themselves aren't going to be made of metal or aluminum and welded together. They're cast on a mold out of fiberglass, much in the same way that you would build a fiberglass canoe. The reason for that isn't because it's cheaper. It's actually about the same cost, but the precision of the surface of the dish is incredibly good. This will be about 20 times better than your typical metal radio telescope that's on the sky today. We also have this very cool folded stainless steel metal technology. Basically, a robot starts with sheets of flat metal, cuts it out with a laser cutter, and then folds each piece like origami style to build these mounts that the dishes sit on. So that allows us to position every dish very, very accurately. It's really important for us that the separation between the dishes is exactly the same, so that the pairs of information between any 2 dishes is redundant, is something that we can calibrate for, and that the dishes themselves are exactly the same. Some of the people here, like Dallas and Ian, spend a lot of their time making possible the prototype of this right now. And just right now, out in the field in British Columbia, we have 2 of these dishes that we're putting on the sky. Some images of it being constructed. You might think fiberglass, like that doesn't reflect light. Of course not. Inside the fiberglass, the very first layer is the thin layer of metal mesh, which is the thing that forms the dish itself. Coupled to that is a feed that's very, very broadband. This is something we've only learned how to do since Chime. It's a feed that's designed so that it can see equally well light that is 1.5 gigahertz or light that is 1.5 gigahertz, 20 centimeters or so, or a light that's a meter long. And again, we've spent a lot of time figuring out how to build these things cheaply. These things are laser cut out of pieces of metal and then assembled with undergraduate manpower to build it. Remind ourselves that people are everything before I go on to the very last thing I want to talk about. Does anyone have any questions or anything? Oh, actually, I'm basically out of time, so I may skip the last one depending on how much else.
Just very quickly, interferometric lensing. This assumes that the 2 paths have the same integrated optical density, essentially over the whole path length, and end is the same, no? Otherwise, how do we test the assumption?
Okay, so Peter's bringing up a good point. Let's say I have 2 different paths, Okay? Then one will arrive after the other, and there's other information that tells me about the lens. But he's pointing out that I might get really messed up, because when they go through two different paths in the universe, the number of electrons along this path could be different from the number of electrons along that path. Right? And so that means their timing is different, and it also means that when I trigger on this thing, I might de-disperse it to the wrong place and not find the second one. It turns out that for the path lengths that we're talking about, where we're talking about nanosecond to millisecond differences, the difference in density of those electrons would have to be just extreme. It's something that we can search over and have tested, but we don't expect it to be a measurable difference in terms of the dispersion measure.
Like
It is
looking at an
degenerated.
extreme object, like you want to look at a small black hole or something like that, which sounds pretty.
Yeah, we aren't
Special
we're getting ridiculously close to them along the lines of traditional lensing, but we're very far away from them in terms of probing, what else is around them. But we can actually solve for that, because we could separately de-disperse them with different slopes, and that would separate the extra time from that from the time delay. Gravitational lensing is beautiful because it's achromatic. No matter what frequency you are, no matter what color you are, you follow the same world line across the universe. What you're talking about is chromatic, and I hate it in some context. It's confusing, but it has a different signature, so I can absolutely separate it. Should I end here, or do you want
It
me to?
would be a good time to wrap up.
It sounds like a great time to wrap up. Okay, great. I was going to tell you in 2 minutes about the South Pole Telescope.
We have 2 minutes.
No, I'm actually not. I'm just going to say, guide you to other people about how the game in that field, which is millimeters, is entirely different. It's about sensitivity and building things that other people can't build, as opposed to taking things that other people have built and bringing them together for a telescope. And the experts in the room here are Joshua Montgomery. Is he here? There he is right there, and McLean Rubel back here. And they, I'm sure, would love to talk to you after, to tell you more about our detectors and how we put them on the sky. There.
Thanks a lot for this really interesting talk. We do have a couple of minutes for questions, so please shoot away. I'll run around and get the microphone in your vicinity if you want to ask a question, so your voice will be heard on the video. I have a very quick one, if it's okay. Is there any effort to make space-based radio telescopes similar to the space-based efforts for optical telescopes and gravitational wave?
Sensors? In terms of the types of measurements that I talked about here and the frequencies that I'm talking about, most of us aren't interested in going to space at all. The exception is if there's somewhere in space that is that it's very hard to see humans, the radio frequency from humans, that would be a great place to be. Cynthia and John don't go to space. They go to Mariana Island in the middle of the Pacific Ocean to get away from people, but they wish they could go to the dark side of the moon. No one thinks our technology and our ability to stamp our stuff is good enough to go to the dark side of the moon yet, but there are groups that study that. It's all different in the millimeter, though, the stuff I didn't talk about, where sensitivity is everything, and we're really mature in the building of our telescopes. And what we spend most of our time on right now is developing our systems to fly on the Lightbird space satellite, which is due to go up in about 10 years.
Okay, thanks. Yeah, I'll just get in your general vicinity.
Why do you only get 2 images? Why don't you get a ring of images?
Oh, we absolutely could. The solutions are such that for lenses that aren't perfect, if you're not perfectly aligned with the object, the equations give you two focal points. If you manage to be perfectly aligned, you can get a perfect Einstein ring and see the whole thing. That actually would be, I think, unobservable for me, because that whole ring would fit. Like, we don't see those 2 images with Chime. They both fall within one of our beams, and what we see is a time lag between them. If you manage to get a perfect Einstein ring, it would be so cool and we'd miss it, because all of the light would be hugely magnified, but it would all arrive at precisely the same time. All the path lengths would be the same. So it's the one thing I don't want to see, but it's so rare that it would, the fact that we're not announcing today that we saw the other one means that we'd be very, very lucky to see that.
Okay, there's a question up at the top here.
This could be just motivated by
Yeah,
me
I'll just
working
hold
on the other half of of your research. But you mentioned that if you wanted to see 21 centimeter light from the very early universe, you'd need a very, very long antenna. Surely why don't you just build one? Like if it's all you need is a wire, can't you just build a Colloquium wire?
So let's say I want to look, so McLean looks at the cosmic microwave background as part of her research. She's looking at a redshift of 1100. And I did have in my example what 21 centimeter light would look like at redshift 1100. It would be 210 meters. And she's absolutely right. I have all the technology I need to go out and build a 210 meter antenna. The problem is the sensitivity to see that is that I would need 7,820 of those antennas all linked together. And I don't have the money to build as many as I made up that number, but it's a tremendous number. I'd have to like tile Earth with it to get the sensitivity. So not only does it have to be big enough to see it, I have to have a low enough noise floor by making many measurements simultaneously to get there.
And David, did you
Yeah, but
want
you could communicate with submarines. But isn't that how they have an antenna in Michigan, which is 100 kilometers long or something?
Is this your question?
No, that's not it. My question was, you kept saying looking at the night sky. Night sky was if I had a nickel for every time you said night sky. Anyway, so when I learned,
By the way,
when I was a
did
student,
my undergraduate thesis with David, it was just like this. He'd come in and say, if I had a nickel for every time you plug that cable in the wrong place.
yeah. But anyway, it's the thing about the, when I was learning astronomy, it was about radio telescopes work day and night, and so in fact, and you see the sun in your maps, right?
Yeah.
So is it really night sky you're talking about, or you just have better background conditions, or what?
Yeah, so Chime observes 24 hours a day whether the sun is up or down. And we of course don't need the sun shining to illuminate things. It's fine to look during the day. The sun is annoying as can be. When it's in our beam, it swamps everything and we for sure throw away the data, but it's only in our beam for a half hour a day. Then it comes out, right? It rises through. Unfortunately, we aren't good enough calibrators yet. We're gonna get this data back. Right now, we are throwing away the data when the sun's anywhere near our beam, basically when it's above the horizon, because the sun comes in from this side, it heats up the telescope differentially, it stretches the telescope in weird ways that we haven't written software to characterize and account for yet. We're lazy, we have a tremendously huge signal in that stacking, so we just throw away all the daytime data. So maybe I did mean to say night sky, but you're right, there's no reason that everything we do can't happen during the day. The sun isn't a problem because it's bright. The sun is only a problem because it's heating things up in weird ways. And certainly with my fiberglass, I'll be way less susceptible to that as opposed to my metal cylinders. So that will be better. And by the way, even though he yelled at me every day for plugging in the wrong cable, it was one of the most fun experiences I ever had.
Okay, with that, let's thank Matt for a great talk.